I'd like to welcome you to this recording in which we're going to discuss sample problem 6.9. This appears on page 464 of edition 7 of Merriam and Craig. Now let's just read through the problem statement. It says that the wheel rolls up the incline on its hub without slipping and is pulled by a 100 Newton force applied to the cord wrapped around the outer rim. Now, to understand this, we need to look at the picture as we have it here on the screen. These are really two views. There's a side view of this wheel, and then this is a view, if you were to view the wheel from, let's say, from the left, if you were to insert the projection plane on the line there, as I'm indicating with a hand here, and you were to project on that plane, this is what you will see. So what we really have is like a groove in the road, and the part of the wheel with the larger diameter is actually going into the groove, and the smaller diameter, the 100 millimeter radius part, is actually the wheel that's rolling on this surface, and the larger diameter, which has a radius of 200 millimeters, that actually goes into this groove, into the road. Okay, now let's go back to the text in the handbook. They say there's a cord wrapped around the outer rim, so you can think of this line here as the cord, but you can think of it like this, as I'm indicating with the hand. The cord is fixed to the outer rim and wrapped around it, and then at the top here it comes off, and this cord, there's a force of 100 Newton applied to this cord in a direction parallel to the road. In other words, in a direction 15 degrees with the horizontal. The road, of course, is an incline with 15 degrees with the horizontal, so this 100 Newtons load on the cord is also in the direction 15 degrees from the horizontal. Okay, getting back to the text. If the wheel starts from rest, compute its angular velocity omega after its center has moved a distance of 3 meters up the incline. The wheel has a mass of 40 kilograms with a center of mass at O. In other words, the center of mass is coincident with the center of the wheel O. And furthermore, it has a centroidal radius of gyration of 150 millimeters. Then, so the first question is to calculate the angular velocity omega after the center of the wheel has moved through a distance of 3 meters up the incline. And then the second question they ask us is to determine the power input from the 100 Newton force at the end of the 3 meter motion interval. Now, why is that a question? Well, initially when this wheel starts from rest, the power input from the 100 Newton force is 0, because the velocity of this force initially is 0. So right at the initial moment, the power input from this force is 0. And once again, it's 0, not because the force is equal to 0, but because its velocity at that point in time is 0. But at the end of this interval, after this wheel is rolled up for 3 meters, the wheel has got a velocity, and then this force also has a velocity. And of course, this velocity increases. It's an ever-increasing velocity. So the power will be determined by the magnitude of the force at that instant in time, which will be 100 newtons, but then also the velocity of the cable at that instant in time. And so that is why they ask us to calculate the power output specifically at the point in time when this wheel is moved up a distance of 3 meters up the incline. Okay, so if we identify this problem, it's certainly a general plane motion problem, because of course this wheel, like any wheel rolling on a surface, there's certainly rotation, but it's not fixed axis rotation, because the wheel itself also, the center of the wheel translates. So it's general plane motion. Now, a procedure that we've used so oftentimes before in Chapter 6, that procedure really applies mainly to force acceleration type problems. And this is not a force acceleration problem, this is an energy problem. So you can think of it as a work energy problem, and I'll discuss in a moment why or how one would recognize that. But because it's a work energy problem, we are not going to follow that procedure. But it is beneficial to still identify the kind of motion that we have. So this first step of classifying the motion as general plane motion is still a valid point. Now, let's just think a little bit about the question, how would we recognize this as an energy problem? And a broad guideline that I think I can give you is that, bear in mind that I've mentioned a number of times in class, perhaps not so much in the recordings, but in class, that we generally do not solve the equations of motion in this module, because the equations of motion normally are differential equations, and they are quite tricky to solve, usually because they are quite nonlinear. So they're not easy equations to solve. And because of that, we normally just solve, in most of our problems that we've done up to now in Chapter 6 at least, we typically solve the problem at a very specific instant in time. You, for instance, calculate a force, or you calculate acceleration, or you calculate something at a specific stance of the mechanism, or a specific position of a wheel, or something like that. There are a few exceptions. The few exceptions were those problems where we employed the integral, where we say omega d omega is equal to alpha d theta. We will use equation 5.1 to integrate omega and alpha and equate the two to each other. This is where you have a situation where you can actually express the angular acceleration of a body alpha in terms of some other angle theta. And the moment you see that you can do that, you know that, okay, I may now use this integration of omega and the integration of alpha with respect to theta to determine omega at various points in the time history. So those kind of problems are kind of exceptions. All the other problems really solve for unknown forces or accelerations or angular accelerations at specific points in time. So this brings us back to the question, well, how should I know that I should use an energy method to solve a problem? This is the answer to this. When you have a problem where clearly you need to solve the problem over a time span, from a certain point to another point in time, and you do not have something like the omega d omega is equal to alpha d theta type of equations, then you should really consider, isn't this perhaps a problem that I can solve with energy methods? Another way of saying this is that, yes, as a general rule, it's difficult to solve the differential equations of motion, these force acceleration type equations. But energy methods, since with the energy method we look at the kinetic and potential energy at an initial point in time and at a final point in time, that actually opens the door to solving problems that would otherwise be very difficult to solve with the force acceleration type equations. Because of the fact that, yes, it's difficult to solve the differential equation of motion, but it's not so difficult to calculate the kinetic energy and the potential energy at an initial point in time and also at the final point in time, and then use the conservation laws or use the work energy equations to then, from you doing that, solve for the unknowns that was asked. So to summarize then, when we need to solve problems that cover a span of time, problems that would even cover a span of displacement like this one, they didn't say anything about time, but they said that we should consider what happens after this thing is moved 3 meters up the incline. Now, yeah, you can think of that, it's going to move 3 meters up the incline, but it's going to do that over a certain time interval from the initial time when O is at its initial position up to the final time when O is 3 meters higher along the incline. So the moment you have a problem that is defined in terms of something that happens over a time interval, chances are good that the way to solve this problem within the context of this MSD 210 course, the chances are good that you need to solve this problem with the energy method. Let's say the only exception would be if you can clearly see that you can derive an expression for the angular acceleration alpha in terms of the angle theta, in which case you can use the omega d omega is equal to alpha d theta type of integration as allowed by equation 5.1. So in this case, we have this problem. We have an initial position, we have a final position 300 meters high up the incline. So this switches on the red flashing light to say, hey, hang on a second, we're not going to use force acceleration equations here. Maybe we can solve this problem using energy methods. Okay, so let's go on to the next slide. And this slide reveals this diagram, which is also in the handbook. But be careful now. This diagram is not a free body kinetic. It's not a combination of a free body and kinetic diagrams. In other words, the diagram on the left. Well, I suppose I cannot deny that this is a free body diagram. But it's not actually as if I'm going to use this as a free body diagram as in the other solutions, as in the typical force acceleration solutions. And then the important point is this diagram on the right-hand side is certainly not the kinetic diagram. It actually shows the wheel at the two positions. You can see that it indicates here it's in fact not two diagrams, it's a single diagram, and it shows the dotted lines, the position of the wheel after its center is moved 3 meters up the incline. So you can see there's a distance of 3 meters. You can see the incline all the way. So they do indicate on this diagram the forces. And the reason why the authors do this, it's actually not so important for solving the problem, but they wanted to make the point here that of all the forces acting on the wheel, namely the weight of the wheel, which since the wheel is, I think it said that it's 40 kilograms. So if you multiply the 40 by 9.81, you get a value of 392 newtons. The weight is through the center of the wheel. Then you've got the normal reaction of the road, and then you've got the frictional force between the road and the wheel, and you've got the applied force of 100 newtons. Now, the point that the authors want to make with this sketch is that of all 4 of these forces, it's only the 100 Newton force and the component of the weight parallel to the road that are doing any work, if we calculate the work. The normal reaction force doesn't do any work because there's no motion in the direction of the normal reaction force. And the friction force, provided that there's no slippage, is also not doing any work. A friction force does do work if it slips. But if it doesn't slip, the friction force doesn't move. Now you shouldn't think of the fact that the contact point actually moves up the incline. That doesn't mean that the friction, you shouldn't think of that as an indication that the friction force moves. It is as if it's a new friction force for every new contact point. The friction force would move if the two surfaces move relative to one another. That motion would be associated with work being done by the friction force. Now, with this problem, we assume that we have got rolling without slipping. I think they've mentioned that in the, let me just see in the problem statement. No, they do not mention that it's rolling with, yeah, they do actually in the first instance. They said the wheel rolls up the incline on its hub without slipping. So because of the fact that we know that the wheel is not slipping, we know that this frictional force is not doing any work. Okay, so when it comes to solving this problem with energy methods, it becomes important to know the velocity of the cable. Now the velocity of the cable will be the same as the velocity of point A. Note that on this diagram they've indicated a point A. It's the point where the cable makes contact with the wheel. They also have a point C, that is the contact point with the road. And of course point O, which was initially given as the center point of the wheel. So the velocity of the cable will be the same as the velocity of point A parallel to the road, the component of the velocity of point A parallel to the road. But if we inspect this, we see that point A can only at that instant in time move parallel to the road. So it's really a case that the velocity of the cable is exactly the same as the absolute velocity of point A. And now the question is, can we determine that? So to determine the velocity of point A, I'm going to use the relative velocity equation that says the velocity of point A is the velocity of the center of the wheel O plus the velocity of A relative to O. Now since both point A and point O lies on the same rigid body, I can say that the velocity of point A relative to O is simply the angular velocity of the wheel, omega, the angular velocity vector, cross the position vector of point A relative to O, which is the vector starting at point O and ending at A. And that vector has a magnitude of 200 millimeters. Now, since I know that my velocity of point A, well, the relative velocity must be normal to the line of connection of A and O. So since VO is parallel to the road, and the relative velocity of A relative to O is also parallel to the road, it means that the velocity of A is parallel to the road, as it's actually indicated in this little velocity diagram here. And because of that, I can actually now neglect the vectors and simply write this relative velocity equation as a scalar equation. In other words, I can claim that the magnitude of the velocity of A is simply the magnitude of the velocity of O, which is indicated as V, right over here and over here. That's, of course, it's a variable V. It varies as the wheel accelerates up the incline because it starts from rest, but it's indicated with V. And then the cross product of omega, the vector omega cross R A relative to O, will simply be in magnitude the length of R A relative to O, which is 0.2 times the magnitude of the angular velocity omega, as it's indicated here in the diagram. In other words, 0.2 omega. Now, since this wheel is rolling without slipping, we can say, well, we have a relationship, a kinematic relationship between omega and the velocity of the center of the wheel. We know that the velocity of the center of the wheel for the wheel that's rolling without slipping is simply omega times the radius in question. And this radius now is the 100 millimeters radius. So we can say omega must be V divided by 0.1. So I'm replacing in this equation the omega with V divided by 0.1. And once I write my velocity of A in this form, it's then very easy to simplify it and to calculate that the velocity of A, or the magnitude of the velocity of A, or the speed of A, is simply 3 times the speed of the center of the wheel. Now the authors have used a different argument to get to this. They've used the argument based on the center of zero velocity. That pertains to a section in chapter 5 that we did not cover in the book. So you can ignore the argument. If you've worked through that theory and if you understand it, it's okay, you can use it. But in general, we didn't actually do it in class, so you don't need to use his argument. You can come to the same conclusion based on a relative velocity argument as I've raised here. But he then also comes to the same conclusion, namely that the speed of the cable is 3 times the speed of the center of the wheel, as we've shown here. Okay, so we need this because we're going to do calculations with energy. So let's then move on. The first thing that we'd like to calculate is the work done by all forces acting on the system other than gravitational forces and forces of elasticity. Now, of course, we've already said that the normal reaction force and the friction force do not do any work. The weight does in fact do work, but the weight is a force of gravity. And please note that I'm not doing the same solution as in the handbook. In the handbook, the authors calculate U12 without the prime. The U12 is the work done by forces, and in other words, including gravitational and elastic forces. I prefer not to calculate that work. I like to calculate the work done by all forces other than gravitational and elastic forces. So I'm excluding my gravitational, the work done by the gravitational force from this. That's why I've got the prime here. That's the notation that we've introduced in chapter 4. So I'm going to ignore, unlike the author in the book, I'm going to ignore the work done by this force. I'm going to recapture this emission by looking at the change in the potential energy. The authors in the book doesn't talk anything about potential energy because they do include the work done by the weight in this work term U1-2 without the prime. Okay, so if I look at the forces doing work here other than gravitational, the only force that's doing work other than gravitational force is the 100 Newton force. And the work that the 100 Newton force does over this 3 meter displacement of the wheel, I'm claiming will be the 100 newtons times the 3 meters times 3, because I'm claiming that if the center of the wheel moves through 3 meters, the cable actually moves 3 times that distance because of the fact that the velocity of the cable is 3 times the velocity of the center of the wheel. You should think of it a little bit like this. If I start pulling on the cable at the initial point in time, at point A, if I now on my cable move at 3 times the speed as the center of the wheel, it will mean that in the same time interval where the center of the wheel is moved 3 meters, I will have moved 3 times that distance because my speed is 3 times that of the center of the wheel. So the distance that the cable moves when the center of the wheel goes through 3 meters is actually 3 times 3 meters or 9 meters, and that's why I've got 3 times 3 here. So it means that my 100 Newton force moves through 9 meters when the center of the wheel moves through 3 meters. And of course that means that the work that is being done by this 100 Newton force is simply 100 times 9 or 900 joules. Okay, so next let's look at the potential energy, and let's define the datum for potential energy right at the center of the wheel at the initial point in time. We claim that this is the level of 0 potential energy, and therefore we come to the conclusion that the initial potential energy is 0, V1 is 0. And then of course we need to calculate the potential energy of our wheel at time point 2 when it's being lifted 3 meters up the incline. So of course the potential energy will then be the mass of the wheel, which is 40, times 9.81, times the height of the wheel at the end of the interval. Now if it's moved up 3 meters at an incline of 15 degrees, the height of this wheel will be 3 times sine 15 degrees above the original position. And if I then calculate this, I get a value of 304.7 joules. Let's next look at the kinetic energy, and we're going to use the kinetic energy expression that we've derived for general planar motion that is given here. Using this, we can say, once again, we're starting from rest, so our initial kinetic energy, T sub 1, is just 0. And then our final kinetic energy, when the wheel is moved 3 meters up the incline, will be using this equation, half times the mass of 40 times Vg squared. Now Vg, we've seen before that the velocity of the center of mass is really this velocity V. And we've since the wheel is rolling without slipping, we can say that the velocity V, or the Vg then, is the radius of 0.1 times omega. So that's what I'm putting inside this bracket here. And of course I'm raising it to the power of 2 because it's Vg squared. So this first term then is my kinetic energy associated with the translation of the wheel up the incline over 3 meters. And then the rotational kinetic energy will be 1/2 times the moment of inertia of this wheel about its center of mass. Now, of course, we don't know the moment of inertia. We only know the radius of gyration, which is 0.15. But we can then calculate the moment of inertia, I sub g, simply by saying that's the square of the radius of gyration of 0.15 times the mass of the wheel, which is 40. So all of this is my moment of inertia, and then omega is the unknown. So omega squared, of course, is then multiplied at the back. So this is my kinetic energy expression, and this allows me to calculate it as a single number in terms of the unknown omega. So it's 0.65 omega squared. You can easily check this calculation. Okay, so now we're going to, I've moved in the wrong direction here. I don't know why that happened. Let me just try to get back where we were. Okay, this is where we were. So the next step is then to apply this energy equation that says that T1 plus V1 plus the work done between time 1 and 2 must be T2 plus V2. In other words, the kinetic energy plus the potential energy initially plus the work done by all forces other than elastic and potential forces over the interval from 1 to 2 must be the same as the kinetic energy plus the potential energy at the end of the interval. So if we now start substituting the values, T1, right here we said that T1 is 0, so I fill in 0 there. V1 is 0, I'll show this in a moment. U12, I'm claiming is 900. Where do I get this? This is what I've calculated here. I've calculated U12 as 900 joules. So I'm just substituting that in there. T2 was calculated just now as 0.65 omega squared, and V2 I'm claiming is 304.7. Let's see where we got this. This is where we got it, and also it shows that V1 is 0. That was previously calculated. So we have this equation, and we have just one unknown in this equation. It allows us to calculate omega as 30.3 radians per second. And clearly, this is the omega at the end of the 3 meters interval, the value of omega at that point in time. So with this, we've answered the first question. Now, the second question, to answer that, I've just calculated the result on this slide. The second equation asked, what is the power at the instant when the masses move 300 meters of this 100 Newton force? Now, for this, we can say to calculate the power, that is, we've seen simply the the dot product between the force vector and the velocity vector. Now, in this case, clearly the force vector and the velocity vector of the force are 100% aligned. The angle between the two is 0. So this cross product of two vectors is quite simple in this case. It's simply the magnitude of 100 newtons times the velocity of the cable. But we still need to calculate that velocity of the cable, which is the velocity of A. And now we can very easily calculate this in terms of omega, because once again, that's really what's explained by this velocity diagram. But it also boils down to applying relative velocity between the point A and the stationary point C. Remember that the contact point C, where the wheel rolls on the ground, is a stationary point. So the velocity of A is the velocity of C, which is 0, plus the velocity of A relative to C, and the velocity of A relative to C would simply be this total distance of 0.3 meters, the distance between C and point A, 0.3 meters, multiplied by the angular velocity of the wheel of omega, which we've calculated as 30.3. So we can say that the velocity of A is 0.3 times 30.3 meters per second. And if we then substitute this into our power equation, that gives us 100 times 0.3 times 30.3. If you calculate that, you can get the value of 909 watt. And that then concludes this example.